This is the part 2 of chapter 3. Let me think about the system variables in the process calculation of chapter 2 and my method for degree of freedom analysis. Chemical reaction equations were considered in both freedom and restrict counting. The number of chemical reaction equation related freedoms is equal to the number of reactants responsible for consumption plus the number of products responsible for generation. Let me give you an example here. There is a system and something is introduced into the system and then going out of the system. The reactor is based on this reaction. Methane with oxygen is going to CO2 and water. So M stands for methane, O stands for oxygen, C stands for CO2, and W for water. In these balanced chemical reaction equations, you have 4 components or compounds are there. 2 of them is categorized as the reactants and the other 2 are products of this reaction. So you would have 2 consumption terms for the system variable, right? Methane consumption and oxygen consumption. And the other 2 are products which would contribute to the generation term. Carbon dioxide generation and water generation. So 4 system variables should be considered in the process calculation of chapter 2 and my method for degree of freedom analysis. So let me say 4 or number of n. N is the number of compounds involved in the balanced chemical reaction equations. So that is for the freedom. Freedom is n or 4. Then let's go to the number of restrict. The number of chemical reaction equation related restrict is the number of stoichiometric coefficients minus 1. You have learned about that. The number and also I can say the number of chemical reaction equation entities minus 1. We have 4 entities and we have 4 stoichiometric coefficients. So the relationship between consumption terms and generation terms are based on 3 independent stoichiometric coefficients. One of the stoichiometric coefficients could be calculated from others. So the independent stoichiometric coefficients are n-1 from the chemical reaction equations. So again, the number of CRE, chemical reaction equation related restrict, should be n-1. So the chemical reaction equation related degree of freedom is equal to n minus n-1 is equal to 1. So 1 for each chemical reaction equation. In the degree of freedom analysis of chapter 2, therefore, the number of chemical reaction equations was counted as the freedom without considering generation and consumption term. At that time, we didn't consider the generation term and consumption term. Only accumulation term was considered. So again, without considering generation and consumption terms as system variables, and without counting the number of stoichiometric coefficients for restrict. So it is the reason. This is the reason why we counted only the number of chemical reaction equation in the degree of freedom analysis of chapter 2. The system variables represented by chemical reaction equations here are actually the extent of reactions, xi. Again, xi, where the extent of reaction is the process variables, while the stoichiometric coefficient and molecular weight are not the process variables, and they are only dependent on chemistry. So from now on, we will consider the xi values or xi parameters. What is that? The extent of reactions will be considered as the process variables, not just chemical reaction equation. The xi represent the chemical reaction equations. Here is the example. Actually, we did it for the degree of freedom analysis, considering xi as the system variables already. Also, this example comes from example 3.5, but there is a little bit small difference. Let me think about that. The title is Urea synthesis from cheaper reactant. Urea can be manufactured from methane, water, nitrogen, methane, water, nitrogen via a pathway requiring 4 chemical reactions. We'd like to design a process to make 90 gram mole per minute urea at steady state. This is the basis for the output stream of desired product from the new materials, methane, water, nitrogen. In this process completely specified, it's time to count the degree of freedom. What is the difference between this 3.6 and the previous example 3.5? So let me draw the block flow or input-output flow diagram. Some process and input and output. We have 3 inputs and we have a lot of outputs considering the unreacted reactant plus some byproducts or intermediates. Actually, in the previous example 3.5, we have assumed that the complete conversion from the raw materials into the desired product plus hydrogen. So we didn't take care of intermediates like carbon monoxide and carbon dioxide plus ammonia as the intermediate. But in this example, we will consider everything in the output streams. So let me start with step A. To define the number of material balance equations. So here we have the balanced chemical reaction equations. So it is better to consider the compounds as the material balance component. So let me try to count the number of compounds. M for methane, W for water, N for N2, and where is the hydrogen? Hydrogen as the byproduct. Plus, there are 3 intermediates, carbon monoxide, carbon dioxide, and ammonia, plus urea there. Okay, that's it. So we have 8 compounds, and you could expect 8 material balance equations. Then let's go to the degree of freedom. So this is for the freedom, and the other thing is restrict. Freedom minus restrict is going to degree of freedom. Then in the previous examples, 3 input sorry. Okay, so the 3 input variables are there and 8 output variables are there for output. 1, 2, 3, 4, 5, 6, 7, and 8 for urea. The 8th variables are urea. And for as these system variables, we have 4 extent of reactions or 4 xis because we have 4 independent chemical reaction equations. plus 0 accumulation. So we have 7 and plus 8 is going to 15. 15 freedoms are there. And let's go to the restrict. Is there any specification for the input? No. So 0 input specification. How about output? We have a single basis for urea output flow rate. So 1 output. Plus there are no accumulation. I mean there are no system variables. So 0 systems. Plus how many material balance equations could be obtained? Of course 8, because 8 compounds was considered as the material balance component. So 8. So totally 9 restricts are available for this problem. 15 minus 9 is equal to 6. It means this problem is underspecified. You should specify 6 more variables. Okay, let's go to the other example. Benzene into catechol. Differential material balance equation with multiple chemical reaction equation at steady state is the some point of this example. So let me think about that. Catechol is used to make pharmaceuticals like L-Dopa and blah 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 vanillin. In the synthetic route to catechol, benzene, propylene combines to make cumin. So let me check what kind of things happen for each reactions. So this is benzene and propylene. They are combined to make cumin. And this cumin, which is considered as the intermediate, is oxidized into cumin hydroperoxide. This is the second intermediate. This cumin hydroperoxide is converted into phenol and acetone. The phenol is also the intermediate, the third intermediate, and the other acetone is considered as the byproduct. And this phenol is reacted with hydrogen peroxide, then it is going to the final desired product, catechol plus water. Water is a kind of the byproduct. Your job is to design a process using this reaction pathway that produces 3,000 kilogram catechol per day. Okay, so that's it. That is our target. You conduct some experiment in a laboratory scale apparatus, very small apparatus, or called a pilot plant. In this example, for the pilot plant or lab scale plant, 13.65 gram more benzene per hour. This is the input flow rate for the benzene and propylene and oxygen and hydrogen are fed to the pilot plant. So let me think about this block flow diagram. Process, and we have 4 inputs, and the specified flow rates of those 4 things are given to you here. The output stream for the plant contains catechol, benzene, blah 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 blah, and the UF analysis is required, and then you should scale up. This small scale of plant is up to 3,000 kilogram day catechol production plant. Okay, then let me start with degree of freedom. So step A, to define the number of material balance equations. So in this case also compounds are the best one for the material balance component. So let me count all compounds here included in 4 different reactions involving some intermediate. So benzene P, B, then propylene P, and cumin CM, and oxygen and cumin hydroperoxide CmHP, and the other thing is phenol and acetone, and peroxide are introduced. So peroxide, hydrogen peroxide, and the final also desired product, catechol plus water. So how many compounds are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 compounds are there. Then let's go to the degree of freedom. 4 input variables, 6 output variables, and we have 4 chemical reaction equation. It means we should calculate the 4 extent of reaction plus no accumulation. It's going to 14 freedoms. And let's go to the number of restrict. The all flow rate for the all components in input are available in the text. So 4 input plus 0 output plus 0 system variables, 0 system performance specification plus 10 material balance equations. So 14 freedom minus 14 restrict is going to 0. This problem is completely specified. Then let's try to calculate those variables in the process calculation. Okay, so here is the process calculation and the block flow diagram and the balanced chemical reaction equation and the step A with the degree of freedom analysis were borrowed from the previous slide. I have said 14 freedom, 14 restricts, and actually we know the information about the 4 inputs. So if I could use the values about 4 input variables, we could reduce the number of freedom from 14 to 10, right? So I have removed the 4 input variables with 4 input information. So the things we want to calculate is 6 output flow rate plus 4 extent of reactions for each reaction. Then also we will use only 10 equations, which are the material balance equations. Then go to the equations. So this process is working on the steady state. So output is equal to input plus generation term, or generation minus consumption term, after you have removed the accumulation term, dNdt. So again, out is equal to in plus generation. Then you have obtained 10 different or independent material balance equations. For example, for the benzene, the output flow rate of benzene is equal to input 13.65 gram mole per hour, which is given to you from the text, minus xy1. The benzene is only included in the first reaction, so xy1 is involved there, and benzene have the stoichiometric coefficient at -1. So the product of the stoichiometric coefficient with xy, the extent of reaction, is going to minus xy1. In the same way, you could obtain the equation for the other component for material balance equation. So we have 10 equations, and then you could calculate the values of 6 outputs and 4 xy's. Then here is the summary tables for the result. So those input variables were given to you from the text for the problem, and you have just solved the problems with those values. then it's time to scale up. This data was obtained from your pilot plan, lab scale pilot plan. But your boss ask you to scale up this small plant to the big production plant at 3,000 the catechol 3,000 kilogram catechol per day production. So let me calculate the scale up factor. Before calculating the scale up factor, I should match the unit of the final scale with the unit of lab scale. So here is the gram mole per hour, here is the kilogram mole per day. So let me change this gram mole per hour at 10.4 gram mole per hour catechol from the lab scale plant to kilogram per day. So 10.4 about the catechol gram mole per hour, then gram mole is going to gram and gram is going to kilogram, with hour is going to day because 20 hour is equal to 1 day. Then finally you could obtain the value in the unit of kilogram per day. That is the 27.5 kilogram per day, which is for the pilot plant. So the scale up factor is 3,000 per 27.5. So the scale up size is about 110x. After you have changed those value and those value from gram mole per hour to kilogram per day, and then by multiplying this scale up factor into this table, you could find the final the scale of production plant. Until now, you have learned about the differential material balance equation, shortly DMB. From now on, I'd like to introduce how to use the integral form of material balance equations. So IMB stands for integral material balance equations. Here is the flow rate as a function of time. Let's think about the first case. So at the very first 2.5 or about 3 hours, you have fed your raw materials into the system at about 2 grams per minute. And then during the following 30 minutes or 1 hour, the flow rate is changed from the 2 to 5 grams per minute, and then 3 grams per minute, and then finally 4 grams per minute or something like that. Sometimes you could increase the flow rate a long time linearly like that. Any the function of times could be imagined for the flow rate. In those situations, you could think about some system over a finite interval from T0 to T final. Total mass entering the system, here M system, is simply equal to the area under the curve of flow rate versus time. For example, here. So it means the system, the mass is calculated by integrating of the curve of the material flow rate, like the integral form of the flow rate with respect to time from time 0 to time final. Here are 4 different integral form of material balance equation. The first 2 things for the mass and the other 2 things for the moles. Let me start with total mass. Anyway, in any cases, The most important thing is accumulation is equal to in minus out plus generation term. For the total mass case, you don't need to think about the generation term. However, for the other cases, including the component mass or total moles or component moles, you should think about the generation term. Again, back to the total mass. Final mass in system minus initial mass equal to integral input minus integral output. How about component? Everything is the same, but you need to think about the integrated generation term. For the mole balance equation, the same thing is working. Let me do practices with understanding those equations. The example 3.8, blending and shipping. At a blending and shipping facility at a large integrated refinery, gasoline from 3 different processes, in this case from reformer, Isomax, and FCC. Those 3 streams are introduced into a storage tank. All of things are gasoline. Also, the flow rate of 3 input streams are specified at 15,400, 18,200, and 10,500 barrels of gasoline per day. You should know that the barrel is the unit of volume. So sometimes it is better to change the volume into the mass or moles. A large tanker or tank ship comes to port to load up. So the ship is coming to the port, and in the port we have the storage tank. The tanker or tank ship holds 60.966 million pounds of gasoline. That is the capacity of the tanker having the gasoline. And it takes 54 hours to pump it full. So the outstream flow rate could be calculated by dividing this mass of gasoline per 54 hours. When pumping to the tanker, it first started, the storage tank contains 154,000 barrels. So at the initial time 0, you have already had some gasoline at this amount. The ship's or tanker's captain is worried that there isn't enough gasoline to fill the tanker. But the supervisor at the blending and shipping facility here tells him not to worry. Who is right? So the question is, do we have enough gasoline in storage tank to fill out the tanker? That is the question. So here you can read some time information like 55 hours, and also more importantly, you have read or you have got the information about the capacity of the tanker size, or the capacity of the tanker to hold the gasoline. So it is the very important hint to force you to use the integral form of material balance equation. So I'm saying about the capacity of the tanker. So let me think about this block flow diagram. We have 3 input, 1 output, and we have the information about those 3 input, also the output. And let me take the gasoline as the component for the material balance equation. Then we have 4 variables, but actually we have all of the information about the 4 variables. So for example, 15,400 barrels per day for the first stream of input, how about the second stream here, third stream, and then the fourth stream, which is output stream. It can be calculated from the capacity of the tanker per the time to be required for filling out the tanker. Then you would have this kind of things. And also one more thing, the input stream flow rate was given to you with the unit of volume per day. However, the output stream was given to you with the mass per hour, mass flow rate. So it is better to change the volumetric rate into the gravimetric rate. So we have four streams are there. And then let's go to the integral mass balance equations. So final mass or gasoline amount inside of the storage tank minus initial is equal to input, of course integral form, minus output. So the change in the system is equal to 3 inputs minus 1 output. And then the flow rates are constant in terms of time, so we have the summation of all flow rates to calculate the total net flow rate. So M1 plus M2 plus M3 minus M4. So this one. And then we should integrate this value with respect to time from 0 to 54 hours. So the mass change would be minus something pound. Minus something pound means something is going out of the storage tank. Then let me check the initial amount of the gasoline stored in the storage tank just before you are feeding the gasoline into the tanker. That the amount of the initial is equal to this amount. So the final amount of gasoline remaining inside of the storage tank after you have finished feeding the tanker, that is the initial plus the initial plus this value, the amount of gasoline going out of the storage tank for filling the tanker. Then the summation is positive, means we have enough gasoline in storage tank. So the supervisor at the blending and shipping facility is right. The second example about the unsteady state situations, maybe batch situation or semi-batch situation. At the award-winning jumping jam factory, cherry jam is produced by chopping up 100-pound cherries and mixing the chopped cherries all at once with 200-pound sugar in a pot. Pot indicates batch reactor, and in this batch reactor at time equal to 0, you have 100-pound cherries plus 200-pound sugar. And then to make the jam, water is boiled off during the process. As the mixture thickens, the water evaporation rate decreases. It means the water evaporation rate is the function of time. Charlie Cherry Pitt, the engineer at Jumping Jam, estimated that the evaporation rate can be modeled as like that, so as a function of time. Time in units of minute in this equation, and the evaporation rate in units of pound per minute in this equation. Then the question is that how long will it take to make 240 pounds of gel? So if you meet the question about the capacity of your system or some time, then it is better to use the integral form of material balance equations. So total amount integral mass balance equation here, and final minus initial is going to the total summation of the input minus total summation of output. So let me start with the initial. We have 100 pound cherries plus 200 pound sugar, so totally 300 pound. And the final mass of the system should be 240 pound, because the question was that how long will it take to make 240 pound of jam at the final time of the operation. So right now we have two values for the left side of this equation. And the other thing is the input term. No input flow for this batch process is 0. And the other thing is output, which is related to the water evaporation rate. So we have only one stream, and I'd like to integrate the function of time for the evaporation rate of water. So this one 2.0 minus 0.03 t from t0 maybe 0 to final time. Actually, this final time tf is the answer for the question how long will it take to make 240 pounds of jam. And then you have this one and this one. Then you could calculate the tf minus t0. This equation is the second order polynomial, so you should have the two solutions. Sometimes one solution, but in many cases two different solutions. So in this case you have 45.6 minutes or 87.7 minutes. You should check whether the solution has the physical meaning or not. So let me put the second solution, 87.7 minutes, to the or this one, evaporation rate equation. By at this time, evaporation is calculated to be negative, like minus 0.063 pounds per minute. However, how can we evaporate at negative evaporation rate? It means condensation, but you are boiling the jam, so we cannot get any negative values from the equation. So the second solution has no physical meaning. And then let's go to the first one, 45.6 minutes. Then this rate is estimated at the plus sign, so this is the answer. I mean, it will take about 45.6 minutes to make 240 pounds of jam. This is the second example for the integral material balance equation, which is the controlled drug release. Patients with certain disease are treated by injection of proteins or drugs into their bloodstream. Upon injection, there is a sudden increase in the protein or drug concentration in the blood to very high levels, but then the concentration rapidly falls. A steadier blood concentration is often desirable to reduce toxic side effects and increase the therapeutic efficacy. Controlled release technology reduces the variability in drug concentration in the blood. With controlled release, the protein or drug is encapsulated in a polymer and released slowly into the bloodstream. This maintains the concentration of drug or protein in the bloodstream at a lower, more constant level. And let's go to question 1. 100 microgram of a drug is loaded into a controlled released capsule. Here is the controlled released capsule, and it has the 100 microgram of drug, and then injected into a patient. So right now we have this capsule including the drug. The drug is released at a rate of 8 to the exponential function of minus 0.1 t microgram per hour. This is the drug release rate. I mean the output flux from the capsule to the blood, where time t is hours after injection. What fraction of the drug has been released after 24 hours? You are reading some information about the time, so it is better to use the integral form of material balance equation. And go to the second question. Once in the bloodstream, the drug is lost at a rate of 3.1 microgram per hour as a result of degradation reactions and elimination processes. How does the mass of drug in the bloodstream vary as a function of time after injection? So in this second question, you should think about the degradation reactions or elimination processes of the drug inside of the blood. At what time is the drug concentration the highest? So what is the maximum? What is the time for achieving the maximum concentration inside of the blood in terms of the drug? Okay, so let me start with the capsule. This capsule is related to the first question. Here is the capsule and we have some drug, and some portion of drug is released from the capsule into the blood. Therefore, I'd like to take the capsule as a system, and we have one component there, drug, and one variables, that is output variables, are available, and the unit of which would be some mass per time, like microgram per hour. Then let me check about the what fraction of the drug has been released after 24 hours. So this is the component version of the integral mass balance equations. So again, accumulation is equal to input minus output plus generation term. So that is our target parameter, which is the final mass of drug remaining in the system or remaining in the capsule and initial amount of drug in the capsule is 100 microgram. So accumulation is equal to in minus out plus generation. In is 0 because no new drug is entering the capsule. And then output flow. So output flow was defined as the like that. So integration of this output flow with respect to t for 1 day, then you could obtain some values about the outflux, the total amount of drug going out of the system. So there is the 72.7 microgram. And is there any reactions or consumptions or generation? For this case, nothing there. So final amount is that the amount of drug going out of the capsule plus the initial amount of the drug existing inside of the capsule. So 27.3 microgram of drug remains after 24 drug release. Then let's go to the second question. So at the solution for the first question, we have taken the capsule as the system for the calculation. Here I'd like to take the bloodstream as the system. And let's go to the component version of integral material balance equations. The initial amount of the drug inside of the blood is 0. So the final amount of the drug inside of the blood is equal to in minus out plus generation term. Of course, there is no output from there is no output of drug from the blood. So the in plus generation term on the right side of these material balance equations. Then let me think about the first term. First term is the drug into the blood, and also we can consider that drug into the blood is drug out of the capsule. And also we have the equation about the drug release from the capsule to the blood. So that was this one. So after integrating the drug release rate from the capsule to the blood with respect to time from 0 to some time, then you could obtain this equation. That is for the input. And how about the generation term? We have some processes for degrading or eliminating the drugs in blood. So that the rate of the degradation or elimination was 3.1 microgram per hour. So put there and integrate the value with respect to time from 0 to time t, then we have 3.1 t. So this is the drug lost from the blood at a rate of 3.1 microgram per hour by elimination and degradation reactions. So this one, the final amount of drug in the blood is determined by the input one minus the degradation rate. Let me draw some plots based on this equation. This is y and t is x. So here is the plot. We could obtain this kind of graph, and you could estimate the time at which the maximum concentration is obtained. Without the degradation process or the function of minus 3.1 t, there are no elimination and degradation of the drug. So it is going up following the exponential function, like 1 minus exponential function of minus 0.1 t. However, after the elimination process is involved in this system, then you could have the shape in which we have some maximum value. The time for achieving maximum drug concentration is about 9.5 hours. So use this equation, then you could obtain that time. Example 3.11, glucose utilization in a fermenter. Yeast metabolize glucose and make ethanol. Humans have exploited this process for thousands of years to make wine, beer, and other alcoholic beverages. Although the chemical reactions are highly complex, the overall reaction can be written simply as glucose is going to 2-ethanol plus 2 carbon dioxide. Besides making ethanol, yeast grow and reproduce, consuming some of the glucose for maintenance and growth. The rate of glucose consumption depends on the number of yeast in the fermenter, as well as the rate of growth of the yeast. So the glucose consumption rate increases as the yeast multiply, of course. We start with a 10-liter fermenter containing 1000 gram glucose and some yeast. So that is the system, which is the 10-liter fermenter containing 1000 gram glucose plus yeast. The fermenter is operated in semi-batch. During fermentation, additional glucose is added continuously at a rate of 20 gram glucose per hour. So this flow rate is fed during the operation in the semi-batch mode. Carbon dioxide is continuously vented to prevent pressure buildup, so no accumulation of CO2 inside of the system. No other products or byproducts are removed. The mass rate of glucose consumption, R.G, gram glucose consumed per hour, this is the mass reaction rate, increases with time as the number of yeast increases. So the mass reaction rate of glucose generation is minus 2.8 exponential of 0.1 t, where t is in hours. About 90% of glucose consumption goes toward ethanol production, with the rest going to support yeast growth. So the glucose consumption rate, or the amount of glucose consumption is going to the ethanol production at 80% and going to the maintenance of yeast at the rest of 90%, I mean 10%. So we have 4 following questions, and system is fermenter, and operation semi-batch mode, and unit is mass or mass flows in this example. The first quantity we should calculate is the rate at which glucose in the fermenter changes with time. We have already know the mass consumption rate of glucose. That was the 2.8 exponential 0.1 t time. So let me build up the mass balance equation about glucose. So accumulation is equal to in minus no out plus generation term. And at time equal to 0, we have had 20, maybe microgram, I'm not sure, 20 as the initial amount, and then the glucose is consumed following minus 2.8 exponential 0.1 t. So this is the mass balance equations. And at time equal to 20 hour, this rate is going to 0. So let me draw a plot based on these equations. Y-axis is the DMDT, the glucose generation rate, or glucose generation rate, and x-axis is the time. So the DMDT, glucose generation rate, is going down, and then finally going to the negative signs. So at the very first time, the amount of glucose is built up, but at 20 hour there are no more consumption and generation. After 20 hour, the concentration or the amount of glucose is dropped down, because after 20 hours we have negative values of the reaction rate. Again, at 20 hour, the consumption and input is well balanced, so 0 net change. However, less than 20 hour, the consumption is smaller than the input, so some accumulation is there. However, after 20 hour, consumption rate is overcoming the value of input flow rate. So depletion is found inside of the fermenter. The second quantity we should calculate is the grams of glucose and ethanol in the fermenter at any time. So we should have the time function of the of the glucose and ethanol amount. Let me start with glucose. So this is the mass balance equations for the glucose. Accumulation dMdt is input minus no output plus generation, and we know the value about the input and generation rate. So this is the ODE, ordinary differential equation, and we know the initial condition. At time equal to 0, we have 1000 gram of glucose in the system. So with using this initial condition and ODE, then you can find the m gram cis function as the as a function of time. So this one, and this equation is going to this plot. How about the ethanol amount? So accumulation is equal to no input minus no output plus generation term. So this is the mass reaction rate for ethanol production. And ethanol production would be closely correlated with the glucose consumption, right? So we know this kind of relationship from the balanced chemical reaction equation. From this balanced chemical equation, what we know is that 2 molecules of ethanol is generated from 1 molecules of glucose. So molar reaction rate per the corresponding stoichiometric coefficient should be constant, and also only 90% of glucose is used for the ethanol generation. Then we have this kind of relationship. Again, mass reaction rate of ethanol production is correlated with mass reaction rate of glucose consumption, and 90% of glucose is devoted to the ethanol production. Also, 2 molecules of glucose, no, 1 molecules of glucose is going to the 2 molecules of ethanol. So you should have 2 here from the ratio of the stoichiometric coefficient, minus sign there. And also you should consider the molecular weight. Then this is the glucose consumption rate, which comes from this one. Then you can find the ethanol production rate as the 1.29 exponential function of 0.1 t. Then with the initial condition at time equal to 0, we don't have any ethanol, then you could obtain this final equation from this ODE, ordinary differential equation. And ethanol amount follows this plot based on these equations. The third quantity we will calculate is the CO2 flow rate out of the fermenter as a function of time. We have 2 different sources for CO2 generation. From the ethanol production, we could have the carbon dioxide. Again, let's go back to this first equation. Glucose is converted to 2 molecules of ethanol plus CO2. So in this first case, CO2 generation rate is closely related to the ethanol production rate. So you have this kind of function of time. And then let's go to the second source of the carbon dioxide. Additional carbon dioxide is generated when glucose is consumed for maintenance and growth of yeast. You know, inside of yeast we have some combustion process. This is a kind of assumption, but it is reasonable. All the remaining glucose reacts with oxygen into CO2 and water inside of the yeast. So glucose plus oxygen is going to the combustion product like carbon dioxide and water. So the carbon dioxide production rate from maintenance is closely related to the glucose consumption rate. However, only 10% glucose is devoted to maintaining the yeast. So 0.1 there, 10% glucose is consumed for maintenance and growth. And those two rate is correlated in terms of the stoichiometric coefficient and also the molecular weight. So you could obtain this function for the reaction rate of the maintenance. So total carbon dioxide generation reaction rate is this one plus this one. So finally this one. And let's go to the balance equation. From the viewpoint of carbon dioxide, accumulation is equal to no input minus out plus generation term. So we have just obtained the function about the generation term, and this is the output with the MDT is 0 because the text of the problem is saying that carbon dioxide is continuously vented so that it does not build up in the fermenter. So there are no more accumulation of CO2. So this is 0. It means output is equal to the generation of CO2. And that is the output flow rate as the function of time. Okay, this is the rest quantity we will calculate. The time when glucose concentration in the fermenter to drop to 0, the amount of ethanol at that point or something like that. So we have already got the function of the amount of glucose and ethanol inside of system as some function of time. So let me start with the glucose. At glucose is going to 0, the time is 42 hours. And for 42 hours is going to the second function of the ethanol production. Then you could calculate the amount of ethanol inside of the system at 42 hours when the glucose concentration is going to 0. That value is 847 gram ethanol inside of the fermenter. This subchapter 3 of chapter 3 is optional. I'd like to say about how to use the linear algebra for solving some problems related to the process calculation. Process flow calculations are based on linear equations of variables. You would have multiple unknowns with multiple equations. Only if number of independent equations are equal to the number of variables, we could solve the problem. That is to say, degree of freedom should be 0 for solving the problems. I'd like to emphasize the independent equations. Here we have 3 different equations. The first one, a plus b plus c equal to 10. Second one, a plus b equal to 5. And the third one is c equal to 5. Can you say that you have 3 independent equations? No, because one of the equations could be obtained from the other 2 equations. I mean the second equation plus the third equation is going to the first equation. So the first equation is not independent of the other two equations. In this case, you should say I have two independent equations with three unknowns. Therefore, you cannot solve these problems, or you cannot specify these problems. Here is the other comment for the linear equation systems for solving the process calculation. I have said the process flow calculation are based on multiple linear equation with multiple variables. So you have this kind of equation set would have. For this example, you have three unknowns and three equations. You can specify this system, and then you can convert those equations into matrix representation. The first matrix is stoichiometric coefficient. I should say coefficient matrix. 1, 1, 1, 1, 2, 2, 2, 3, minus 4. So coefficient matrix for unknowns. And the second one is variable vector. You could find the unknowns you wanna calculate. And on the right hand side of this matrix representation, you could find the constant values 6, 11, 3 on the right side of the equations is going to the right side of matrix representation, which is called constant vector. So the multiple equations, actually multiple independent equations of multiple variables can be represented by a by x equal to b. That is the matrix representation. After you made the matrix representation from your processes, then you could solve the problems. That is to say, you could obtain the values of unknowns. Gaussian elimination method to solve the problems of multiple linear equations with multiple unknowns. Actually, you have learned about Gaussian elimination from chapter 1. The core of the core of Gaussian elimination method is to make reduced triangular form. What is the reduced triangular form? Look at this triangular form. Non-zeros on the diagonal and zeros below the diagonal, and then you could easily obtain the values of the unknowns. So please go back to the chapter 1 and read the content about the Gaussian elimination method. Also, this is about the Gaussian elimination method for making the balanced chemical reaction equation from chapter 1. And then let me use the matrix representation with Gaussian elimination for solving some problems for the generation consumption analysis. You have learned about how to synthesize reaction pathways in generation consumption analysis in chapter 1. In processes based on multiple reactions, intermediates can be removed by controlling wave factors chi of chemical reaction equations. Can you remember chi? You have learned about the weight factor chi for chemical reaction equations in chapter 1. Please review the part about chi. Then the process can be optimized in terms of RP molar ratio, atom economy, and process economy. So this is the governing equation to find the values of appropriate wave factor for chemical reaction equation. The wave factor is chi for the corresponding chemical reaction equation K. In chapter 1, we have made the weighted sum of stoichiometric coefficients of intermediates of our interest zeros. Then you could erase or kill the intermediates in the output product. In that case, let me try to use matrix mathematics to find the correct values of chi. Here is the detailed description about how to use how to make the matrix representation for the multiple chemical reaction equation case. So I please read it thoroughly, and I'd like to go directly to the example. Here we have 1, 2, 3, 4, 5, 6 equations there, and then the first thing I'll do is to make the stoichiometric coefficient matrix. So list check the compounds involved in those 6 reactions and list those reactions on the column like that. Oxygen, nitrogen, methane, blah 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 blah. Go to the desired product, nitric acid. So you have 11 compounds involved in those 6 chemical reaction equations. And then list the chemical reaction equation on the row R1, R2, R3, R4, R5, R6. And then please fill out the empty spaces of the matrix for stoichiometric coefficient. For example, oxygen of reaction 1 have -1 as its stoichiometric coefficient. How about nitrogen for the reaction 1? 0, because you cannot find nitrogen in reaction 1. However, nitrogen in reaction 3, the stoichiometric coefficient of nitrogen is going to -1, something like that. So you have right now 11 by 6 matrix there. You know, for solving the problems, the number of columns should be the same as the number of rows, but we have 11 by 6, so I should try to reduce the number of rows. Then let's try to find single entity rows like 0, 0, -1, 0, 0, 0. So here is the single entity. How about methane, -2, and the other thing is 0. CO2, the second term is 1, but the other is the others are zeros or something like that. The same thing for the nitric acid. Single entity law indicates this law is about the compound used only for the reactant or used only for the product. They are not the intermediate. So you cannot remove those compounds even after the adjusting the weight factors. So it would be better to remove the single entity rows. 1, 2, 3, 4. Then right now we have 7 by 6 because you have killed 4 rows. Then we have right now O2, H2O, CO, hydrogen, ammonia, NO, NO2 or something like that. And let me focus on the first 2 compounds, oxygen and water. Oxygen and water, they are very cheap from the viewpoint of reactants, and they are not toxic from the viewpoint of product. So I don't care about the existence or the amount of oxygen and water. So I'd like to kill those rows. So right now 5 by 6 matrix. Okay, so right now the number of column is larger than the number of rows. So let me reduce the one of the columns. We have 6 reactions, and let me fix the first reaction as the basis. It means the weight factor for the reaction 1, chi1, is equal to 1. Then this column is going to the right hand side of the matrix representation. So I have killed these 2 rows, and this one is going to the right with the negative sign. So -2, -4, 0, 0, 0 on the as the constant vector b. And this part 5 by 5 coefficient matrix is going to here, and the variable vector consists of chi2, chi3, chi4, chi5, chi6. Of course, chi1 is equal to 1. By solving these problems, maybe by using the Gaussian elimination method or something, then you could obtain the values of each weight factors. And by applying the weight factor to each reactions, by applying the weight factors to stoichiometric coefficient of each reactions, then you could build up the final table of the stoichiometric coefficient. In this case, the weight factor of reaction 2 is 2, so -2, -2, +2, +2, which coming from the -1, -1, +1, +1, something like that. So that is the application of the matrix mathematics to how to synthesize the reaction pathways in generation consumption analysis. Here is the homework, problem 3.12.26. Sorry. That's it for the chapter 3 about the mass balance equations.